In this problem, we have two very long lines of charge. One line of charge lying on the x-axis, that one is positive charge distribution, and another line of charge with negative charge parallel to the x-axis located at y equals 0.400 meters. In part A, we'd like to calculate the net electric field at a point in midway between the two lines of charge, that is at y equals 0.200 meters. I call that point A in the picture. So first, let's figure out what the direction will be for each electric field due to each line of charge. Now the positive charge distribution, which I call lambda 1, will create an electric field away from itself since it's positive charge. So that will be pointing up, the electric field at point A that will point up. That's E1A in the picture. On the other hand, the negative charge distribution on top, which I call lambda 2, will create an electric field towards itself. At point A, that will be again pointed upward. So both E1 and E2 at point A will point upward. Net electric field at point A will be the vector sum of these two electric field vectors. Now I have also labeled the distances in the picture. R1A is the distance from the positive linear charge distribution to point A, and R2A is the distance from the negative linear charge distribution to point A. Numerically, these have the same value and they're equal to 0.200 meters. Now let's go ahead and set up our equation. For each linear charge distribution, we are going to use the formula of the electric field magnitude due to very long charge distribution with charge density lambda at a distance r, and the formula is equal to 1 over 2 pi epsilon 0 times absolute value of lambda divided by r. Now the reason why I'm using absolute value for lambda is because this is just the magnitude. We have already determined the directions that we are going to use in our vector equation, but this formula just gives us the magnitude. So when I plug in the values for R1 and R2, I'm going to plug in the positive values, the absolute values. And here I have set up my vector equation. Net electric field vector at point A is equal to the electric field vector from charge distribution 1 plus electric field vector from charge distribution 2. So I expressed each vector as its magnitude times j hat. Both are pointing in the positive direction, so both have plus signs. And in the next step, I substituted the formula for electric field magnitude due to linear charge density lambda. Again, I'm using the absolute values for linear charge densities, lambda 1 and lambda 2. Now, there are a lot of common factors. In the next step, I factored out those common factors, 1 over 2 pi epsilon 0, and overall, both I have a factor of j hat because, again, this is a vector equation. Now let's go ahead and plug in the numerical values and calculate the result. Here I have substituted the numerical values, keeping 3 significant figures, and the result is the electric field vector at point A has magnitude 6.47 times 10 to the 5th newtons per coulomb, and it points in the positive y direction. In part B of the problem, we're calculating the net electric field at point with coordinate y equals 0.600 meters. I call that point B, and let's take a look at the electric field vectors. The electric field vector due to a linear charge distribution 1, again pointing away from the charge distribution, is pointing up, whereas the electric field vector due to linear charge distribution lambda 2, because this charge distribution is negative and the electric field vector should be pointing towards the charge distribution, now this electric field is pointing down. So the two electric field vectors point in opposite directions. Again, I labeled the distances R2b and R1b. R2b is equal to 0.200 meters. Now R1b, which is the distance from charge distribution 1 all the way to point B, is equal to 0.600 meters. Now let's go ahead and set up our equation. It's going to be very similar, except that vector E2 will have a negative sign. Here I have set up the equation for net electric field vector at point B. One main difference is that now we're subtracting E2. Also note that instead of R1A and R2A, we have distances R1B and R2B. Again, let's factor out the common terms. Here I have factored out the common terms 1 over 2 pi epsilon 0 and j hat. Let's plug in the numerical values and calculate the final result. Here's our final result. The electric field vector at point B has magnitude 7.19 times 10 to the 4th newtons per coulomb, and it points in the negative y direction.